This is a lecture about section 4.3, or undamped harmonic oscillators. Forced harmonic oscillators. Undamped, not underdamped. Okay, so we're assuming that we've got no damp in here now. Of course, that's almost always unrealistic, though there are plenty of situations where the damping is real tiny. And maybe we can get some insight about cases where the damping is real tiny from this undamped case. So that would be the situation where you have my prime. I'll go ahead and take m to be 1. There would be no b times, my double prime, excuse me. I'll take m to be 1. There would be no b times y prime term, because that would be the damping term. But there will definitely be a ky term because of the fact that it's a spring, a mass on a spring. If we didn't have a ky term, it wouldn't be a mass on a spring. Hooke's law needs to be in here. And just like in the video about section 4.2, I'm going to consider a periodic forcing function, a cosine function. I'm going to keep the frequency of this cosine function arbitrary. I'm going to call the angular frequency omega. I know there's a big temptation to call that w, but technically it's an omega. Try to make it a little curvier than a w. I used to make my w's this way, by the way. Now I make them more like that so that I don't confuse them with omegas. We can also consider the case with the sine of omega t. Technically speaking, omega is the so-called angular frequency of this forcing function. The actual frequency would be omega over 2 pi, the reciprocal of the period, which is 2 pi over omega. And you do typically speak in period when you're talking about time for your independent variable. If the independent variable were a length, then you typically call the period a wavelength. They would be the same concept. But with time for your independent variable, we'll call that the period. Period, again, it would be 2 pi over omega, and the frequency would be omega over 2 pi, typical units. If t is in seconds, then the frequency would be in 1 over seconds, which is called hertz. I'll also consider the initial value problem, y of 0 equals y prime of 0 equals 0. That's going to keep things simple, ultimately, by considering that initial value problem, though you could certainly modify things in a more complicated way for other kinds of initial value problems. But I'm going to keep the k and the omega as parameters. K a positive parameter, and, well, I guess omega could be positive or negative, but you might as well consider it to be positive when you've got a cosine function here. If it were negative, since cosine is an even function, it really doesn't give you anything different. It is a forced equation, so we have to find the natural response first, the solution to the corresponding homogeneous equation, where 0 is on the right side. You'd get your characteristic polynomial to be s squared plus k equals 0, and assuming k is positive, that's actually going to have imaginary roots. It's going to have roots plus or minus I times the square root of k is positive. It would be actually square root of k, plus or minus I times square root of k. I'd initially write that as square root of negative k, but then thinking of negative k as negative 1 times k, I'd pull out the square root of negative 1 to get an I here and get this. And ultimately, by using Euler's formula and peeling off the real and the imaginary parts into a linear combination, you'll get your YH to be, well, maybe I should use something besides k. I'll use a c this time. C1, an arbitrary constant C1, times cosine of square root of k times t, plus another arbitrary constant C2 times sine of square root of k times t. Again, you would derive that by writing this a complex solution e to the I square root of k times t, use Euler's formula, pick off the real and the imaginary parts, ignoring the I, put arbitrary constants in front of those, and then add them, forming a general linear combination, and that will be your YH. Coming over to this side of the board, just like in the section 4.2 video, we have to complexify the original equation. We have to consider the so-called complexified equation as a nice way of helping us find a particular solution to the original non-homogeneous forced equation. We need to find the forced response in this way. You can do it without complexifying it, I did mention in the section 4.2 video, but this does provide a nice way of doing it because what we're going to see is the undetermined coefficient in front of our guess will determine the amplitude and the phase shift of yp. Although in this case we'll actually see that with an undamped oscillator we actually get a real number for that coefficient. So what is the complexified equation? It's the same left-hand side, but the right-hand side, if you've got a cosine of omega t or a sine of omega t over here, will be e to the I omega t. So this original right-hand side would be the real part of that new right-hand side for this new complexified equation. If I have a sine of omega t here, that would be the imaginary part of the right-hand side of the new complexified equation. If I had some constant in front of the cosine of omega t, like a 2 or a 3, I'd want to carry that constant over here. The constant is 1 effectively here, so I'm carrying the 1 over. That's my complexified equation. So now I guess a solution to this, and I called it yc. The real part will end up being yp. An undetermined coefficient times e to the I omega t. The derivative of that will be I omega a e to the I omega t. The second derivative of that, the I squared, gives you -1. You get a negative omega squared. I'm just using the chain rule a couple times here. E to the I omega t. Showing up okay? All right, great. Plug that into the differential equation, the complexified equation. Negative omega squared e to the I omega t is the second derivative, plus k times the function, k times, I guess I forgot my a here, didn't I? A in there, and an a down here. Down here we got k times y, k times a e to the I omega t. You want that to equal the right-hand side for all values of t, and factoring out as much as you can on the left-hand side. You see that you can factor out an a and an e to the I omega t. Means that you want to choose the a so that this product is 1. In other words, a is going to be the reciprocal of that thing. A is going to be 1 over k minus omega squared. And that will be a real number. K and omega are real numbers. That'll be a real number. I guess the only thing we have to watch out for here is dividing by 0. We wouldn't want omega to equal square root of k. That would be evidently a different kind of case to consider. But let's assume for the moment we're not dividing by 0. That's our a for the yc. We ultimately want the real part of yc to get a yp for this equation. Again, this is a real number back here. Plugging it back in and using Euler's formula, actually I'll just write this out from Euler's formula. It would be a cosine of omega t plus I a sine of omega t. The real part is what we want. Plug in the a there and you've got your yp. Yp is going to be 1 over k minus omega squared times cosine of omega t. Adding yp to yh gives us our general solution to the original non-homogeneous equation. I'll write that out here. So the general solution, arbitrary constant c1 times cosine of square root of k t plus another arbitrary constant c2 times sine of square root of k t plus yp that I found over there, 1 over k minus omega squared cosine of omega t. If the original right-hand side had been a sine of omega t, then we would have taken the imaginary part over there, and the only difference would have been a sine of omega t right here. We do, to keep things simple, want to solve this initial value problem where both the function and its first derivative are 0 when you plug in t equals 0. The function being 0 when t is 0 is going to give us this equation. Cosine of 0 is 1, so you get a 1 there. You get a 0 there because sine of 0 is 0. We'll get a 1 over k minus omega squared. So C1 is going to be the opposite of that, negative 1 over k minus omega squared. You could also write that as 1 over omega squared minus k. Taking the derivative of this, I'm just going to do this in my head, by the way, so listen real carefully and maybe try to write it down as I talk. Taking the derivative of this and using the fact that the derivative at 0 is going to be 0, the only thing that's going to give me a cosine term when I take the derivative is the middle one. This will differentiate to something times sine. This will differentiate to something times sine. This will differentiate to square root of k times c2 times cosine of square root of k times t. When you plug in t equals 0, you'll have a 0 here, a what will be a c2 times square root of k here, and a 0 there when I take the derivative and plug in t equals 0. And ultimately, what that's going to mean is the c2 has to be 0. You're going to get the equation c2 is 0. So my one particular function that is a solution of this initial value problem, I can write like this. I'm going to factor out the common factor of 1 over k minus omega squared. I'm looking up here, realizing the c2 is going to be 0. If I factor out what's common, and the c1 is really, I want to think of as negative 1 over k minus omega squared, what I'm going to end up with then is a cosine of omega t minus a cosine of square root of k times t. So that would be one way to write the solution of the initial value problem. Now the fun really begins, okay? What we would like to do is we'd like to ultimately understand that phenomenon of resonance. And resonance most easily occurs when you have no damping or a very tiny amount of damping. When the omega and square root of k are very, very close to each other, but not quite equal, at least in this kind of analysis. When omega equals square root of k, that's where we were dividing by 0 earlier, and so this analysis doesn't quite work. Technically speaking, when you've got perfect resonance, omega equals square root of k, then things are perfectly in resonance. But we're not going to quite consider that. We're going to ultimately want to think about what happens here when omega is almost equal to square root of k, but not quite. Now, you could certainly use Mathematica or use your calculator to try different values of omega and k here and look at the graphs. You could also use some trigonometric identities to help you understand why the graphs look the way they do. I'm not saying what they look like yet. What I'm going to show you is a neat way to use complex number arithmetic to help us understand the graph of this function. I'm going to try to avoid using the computer here at first. This is a bit tricky, okay? So you really need to pay attention. It's an example almost exactly like this in the book, except they take k to equal 2. I'm leaving the k as arbitrary. To simplify the notation, I'm going to call this a, and the book does that too. That was the undetermined coefficient that we already solved for. What I'm going to do is I'm going to realize that this function, a times cosine of omega t minus cosine of square root of kt, could be thought of, it's not real clear why you'd want to do this, but certainly could be thought of by Euler's formula to be the real part of this function, a times the difference e to the I omega t minus e to the I square root of kt. Okay? Think about that. Imagine using Euler's formula to work backwards, perhaps. Don't focus on the RE, just focus on this. Cosine of omega t there, plus I sine omega t, and then a minus quantity, cosine of square root of kt, plus I sine square root of kt. Combine the cosines would be the real part, and we ultimately do want to take the real part to get that thing. A is a real number, so we don't have to worry about that. This would be true. Now I'm going to do something kind of strange. I'm going to introduce two new parameters. Alpha is going to be the average of omega and the square root of k. And beta is going to be essentially half the distance between them. Now, I'm going to write it like this. It's technically speaking to be half the distance between omega and square root of k. I need to put absolute value signs in there because omega might not be bigger than the square root of k. But I'm going to leave it like this. So technically, it could be a negative number. It could be negative of half the distance between omega and the square root of k. It depends on their particular values. Notice here that if I make these substitutions, that if I add these two things together, alpha plus beta, think about what would happen if you added these two things. The square root of k over 2's would cancel. Or if you like, you add the fractions, keep the common denominator. You have the square root of k and a minus square root of k canceling. You'd also have an omega plus an omega, 2 omega. Divided by 2, you just get an omega. And if you subtract one from the other, alpha minus beta, if you do it this way at least, think about what happens. Subtract the two fractions. They already have a common denominator. You would have an omega minus omega, canceling, and a square root of k minus negative square root of k, giving you 2 square root of k over 2 simplifies to square root of k. So if I make these substitutions, then alpha plus beta equals the omega, and alpha minus beta equals the square root of k. I know the point is not clear yet. We'll come to that. I'm sure it took somebody a little bit of trial and error to realize this at first. So let me go ahead and make the substitutions in terms of alpha and beta. Since we've just found that omega is alpha plus beta, we can replace the omega with alpha plus beta. And then square root of k is alpha minus beta, so looking up here and down here at the same time, wide view, we can replace the square root of k with alpha minus beta. Again, it's still not very clear where we're going with this. We're getting there, okay? Now, properties of exponents, okay? We used that in the last video to help us see that the complex let's see, what did we use it for? We wrote A in its polar form and then combined it to write YC in a nice form that allowed us to see that the, trying to remember what I did, I think it was the real part of that, for that example. We ended up being able to see why the amplitude and phase were as they were. That was the point. Here we again use rules of exponents. This thing here can be written as e to the I alpha t times e to the I beta t. And this thing right here can be written as e to the I alpha t times e to the negative I beta t. And there's a common factor of e to the I alpha t. That's why I made the substitution in the first place. That can now be factored out. So we have a e to the I alpha t times this difference, e to the I beta t minus e to the negative I beta t. Okay, purpose still not clear, I'm sure. Again, we're getting close. Now I'm going to go use Euler's formula. Again, I used it up here. I'm going to use it again, but not on the entire thing. I'm only going to use it on this difference here. We've got the real part of A times e to the I alpha t. Using Euler's formula on the difference, I get a cosine of beta t plus I sine of beta t. That's the same as this down there. Now subtract what you get when you use Euler's formula here and carry the negative sign into the beta t. So I have minus cosine of negative beta t plus I sine of negative beta t. Cosine is an even function, so cosine of negative beta t is the same as cosine of beta t. Sine is an odd function, so I sine of negative beta t is negative I sine of beta t. And now I get a little bit of cancellation. The cosine of beta t minus cosine of beta t's cancels. I guess I ultimately do need to use Euler's formula here too, because I'm going to get this whole thing is going to simplify to plus 2I sine beta t. And now use Euler's formula here. This is cosine alpha t plus I sine alpha t. Now, ultimately, I want the real part of this thing. My whole goal here is to try to find an alternative way to write y. Okay? My solution of the initial value problem. It's the real part of this thing. I got the A, I've got this thing, and I got times that thing. What's the real part going to be? A is real. I've got an I there. The real part is going to come from multiplying this thing times the I sine alpha t here. And I'll get a negative sign because of the I squared. So ultimately, the real part of all this is negative 2A sine alpha t sine beta t. Okay, that was a lot of work, a lot of tricky work to write y in a different form. This function right here is the same thing as this function when you make these substitutions. They're the same function. Don't look the same, but they are. It is possible, certainly, to use trigonometric identities to see this, to go from here to here and avoid complex numbers altogether. But, trigonometric identities are kind of hard to remember. They're sometimes hard to know when to use them. And this is more fun anyway. So maybe that's a good enough justification. Maybe. I'm going to go back to omega and square root of k now. A again is, oh, I forgot. Was it 1 over omega minus k squared? Or the other way around? Do you remember? I erased it, I think. Well, you think it might have been the other way around? Let me think here. We're using it for, we took YC, A e to the I omega t. The second derivative of that was negative omega squared. A e to the I omega t, we factor out A. Yeah, it's like omega squared minus k, or else the other way around. Omega squared minus k. It's either this, or else it's got k minus omega squared on the bottom. I don't remember. Okay, so this is with uncertainty there. Okay, but that won't be the point. We won't have to worry about that, because the point is going to focus on these sine terms. Alpha was omega plus square root of k over 2. And beta is omega minus square root of k over 2. Now we do some thinking. If omega is real close to square root of k, this thing is real close to 0. The angular frequency and the regular frequency is real close to 0. The regular frequency here is going to be this thing in absolute value divided by 2 pi. This thing has frequency absolute value of omega minus square root of k divided by 4 pi. Real small if indeed omega is close to square root of k. What does small frequency mean? It means it's a wave that oscillates slowly. The period is large. On the other hand, this term is going to have a much higher frequency, especially the closer omega gets to square root of k on a relative scale. It still might not be a huge frequency, but on a relative scale, the frequency of this part will be much bigger. I guess I don't need absolute value signs here because those are positive. Divide that thing by 2 pi, you'll get a 4 pi on the bottom again. Again, if omega is real close to square root of k on a relative scale, this is going to be much bigger. Much faster oscillation, much smaller period. What does this tell us? This function, this solution, is somehow a combination of these two frequencies. It's a product of them. Let's see if we can use the computer to understand in a couple different ways what's going on. Well, it was at this point in the video that I went to the computer and tried to illustrate this process, what this solution looked like on the computer, but I made lots of mistakes. And so what I'm doing right now is I'm filming in my office, as you can see. There's my office. And I'm going to show you what I should have shown you before on the video, though you will never really get a chance to see it since I'm editing it out. Let's look at my computer here. Thrill cam a little bit first. Alright. Hopefully that didn't make you too dizzy. What I want to illustrate here is that, first of all, that these two forms of the solution to that initial value problem are the same. So you can see this first function here is the way that I wrote my solution to the initial value problem initially. And the second function down here, going on to the next line, is the second way that I wrote it after I used the tricks of introducing the extra variables alpha and beta. So the first thing we want to see is that these functions are the same function. And I've got both of these functions in here. For certain values of the parameters omega and k, I picked omega to be 2 and k to be 3.9, right there. Notice in doing so that I'm picking omega to be close to square root of k. So that's going to be close to resonance. And this is an illustration of the so-called beating phenomenon. This is a graph of the solution to that initial value problem. And it goes on forever and ever with this kind of pattern. It's a combination of fast and slow oscillations. Here you can see them both. The quick up and down, that's the fast oscillations. In the form of the solution up here, that comes from this term right here. That's the fast oscillations. The slow oscillations, the overall up-down pattern that goes more slowly, has a smaller frequency, comes from this one. The frequency of that one again being the absolute value of omega minus k, minus square root of k, divided by 4 pi after you divide that thing by 2 pi. And the fast frequency being omega plus square root of k over 4 pi after you end up dividing that thing by 2 pi. So once again, when omega is close to square root of k, you get this phenomenon, this beating phenomenon of fast oscillation sort of enveloped in a slower oscillation, like this. I should have also added in there, this is a break, that the fact that I'm graphing both f and g in here in the same plot and I'm not getting different graphs is illustrating that they are the same function. And I forgot to say that. Now back to the original video. Why does that happen? Well, there are two ways you can look at it. One way you can look at it is to go back to the original form of the solution and take apart its pieces. F was this function plus this function. I have the minus sign in there so that it really is the sum of those two functions there. And I've got to manipulate this as a manipulate command here. And what I'm going to do is I'm going to set k to be, say, about, well, let's open this up a little bit here. Set k to be 4. Real close at least. And then let the omega change, and watch what happens to the graph. Now as I change omega, something's happening down there. Here we go, we're getting close to the moment of truth. Omega's getting real close to the square root of k now, and look what's happening to the solution. The solution is what's in blue, actually. And actually the graph is not real good. Okay, well if I stop it there, that's better. Omega is pretty close to square root of k here, and you can see this beating phenomenon seems to be happening with the blue curve. Why? Well, the red and yellowish curves are supposed to be illustrating why. When the red and the purplish and yellowish are out of phase like they are over here, then their sum is close to 0, and so the solution curve, the blue one, is close to 0.
When you move over this way, they are in phase, they're overlapping, and that makes their sum much bigger. The blue curve, the solution curve, is much bigger. So when they're just barely, they have barely different frequencies, that's what causes this to happen. Sometimes they're in phase, sometimes they're out of phase. So that's one way to look at it. Another way to look at it is in terms of the second representation of the solution as this function times essentially this function here. Now ignore that 5 that's in front of it. I just put that in there as an extra thing to make it so that we can see that better. So it's not a sum in this case, it's a product. If I graph these things, and once again I'll let k be close to 4, and let omega change. Let's see, okay, again the blue is the solution. By graphing the product, I also graph a positive 2 times that beating factor, the fast oscillation, or excuse me, the beats is the slow oscillation. I graph the slow oscillation up here with a negative 2 in front of it, and the slow oscillation with a positive 2 in front of it down here, to make it sort of an envelope around the overall slow oscillation. You can see how that envelope changes as omega changes. The purplish curve is supposed to be representing the fast oscillation, and you can see the frequency of the purplish curve is the same as the solution curve, the blue curve. So this is illustrating how the blue curve can be thought of in terms of fast and slow oscillations. Again, the slow oscillations are the beats. When we're at resonance, basically the solution blows up. That's something you should look up in the book. You have to add an extra factor of t in front of your guess, and that's essentially what causes the solution to blow up when you're at resonance. And you should know how to do that. You should again know how to find the actual frequencies of the slow and fast oscillations, the slow being the beatings, the beats, and find their periods by taking the reciprocals of the frequencies, and understand how to do the complex number arithmetic to verify this. And let's see, anything else? I was going to say something else, but I can't remember. If I think of it, I'll send you an email about it. And that'll be the end of this video. Oh, I did want to say one more thing with regard to real life, that resonance does occur in real life. And I showed you this before. This illustrates it when you've got external force, where the natural frequency and the frequency of the external force are very close together. That's the plunger at the top. It's close to the natural frequency of the mass spring system, and the oscillations can get bigger and eventually get smaller again. I think I didn't quite set my damping to 0 here. That might be good. You can see the fast oscillations, but it should go back to slow lower oscillations to how it's enveloped in the overall beating frequency. That's what this is illustrating. So it is a phenomenon that has to be taken into account in various kinds of systems in real life.